Hello everyone, and welcome back. Today we're going to be continuing our exploration of continuity of real-valued functions and introduce two different types of continuity, often referred to as uniform and Lipschitz continuity. So what exactly did we mean by continuous at a point and continuous on a set? So what did we do? So let's assume, again, as usual, we're going to let f map a to r, and we're going to say that f is continuous at a point if for any epsilon greater than 0 there exists a delta such that if x minus a is arbitrarily small, for any x in a for a particular a in a, then the distance between their images under the function f is arbitrarily small as well. And if f has this property for all a in the set, then we say that f is continuous on the set. And the definition for uniformly continuous is very, very similar with a couple of subtle differences. So as usual, f is still mapping a to r, and we say that f is uniformly continuous on a. So notice that we don't even begin to define uniform continuity at a point. Uniform continuity is defaultly defined on a set. So that's the first important difference between uniform continuous and continuous functions. If, again, for any epsilon greater than 0, there exists a delta greater than 0, so the premise of this statement is practically the same, such that if x minus y is arbitrarily small for all x, y, and a. Now here's the very important difference. Remember, for continuity, we're looking at all of the points around x is equal to a. So that's just a neighborhood for a particular point. But for uniform continuity, what we're doing is we're taking two arbitrary elements in the domain. So if you take any arbitrary elements in the domain and make them arbitrarily close to each other, then their images are arbitrarily close to each other as well. So one could ask, is it possible to define uniform continuity at a point? I would have to say no, because we're required to look at arbitrary elements in a set, and obviously x being equal to y is defaultly, 0, right? So 0 is less than delta. Obviously that's okay, but it doesn't really tell you much about anything because obviously f of x minus f of y would also be 0 as well. Right? So uniform continuity appears to be talking about the continuity of a function on a set, and keep in mind that this epsilon and this delta depend on any x, y in the set, right? So it could be a different delta for the basic definition of continuity. So if you were to pick A1, you would have, say, delta 1. If you were to pick A2, you would have a different delta 2. But for uniform continuity, you practically have the same delta for any point x, y in that set, provided that it is uniformly continuous on that set. So it appears to be that uniform continuity is a stronger form of continuity, and is that truly the case? And that obviously motivates the very first theorem. So if f is uniformly continuous on a set A, then f is continuous on that particular set A. And I'm just using abbreviations, uniformly continuous and continuous, because we're going to be using these words a lot today. So, how are we going to prove that uniform continuity implies just basic continuity? So, if we pick y to be equal to a, so keep in mind x and y must be arbitrary elements, so it has to be true for all x, y, and a. So I can pick a particular one. In particular, I can choose y to be equal to a, and let's assume that a is a particular point in your set. So that means that f is continuous at each a in A, which means that f is continuous at A, or on A, preferably said. Right. So actually the proof of that is very trivial because it's practically the same exact definition, but a little bit more stronger. Now, we already know what it means for a function to be continuous, at least in the graphical sense, for single variable calculus functions. So let's see if we can come up with a few examples on uniform continuity for some basic functions that we already know, and see, are they uniformly continuous? Are they continuous but not uniformly continuous? Questions like that. So let's suppose a very important function. Let's assume we have the function that maps the open interval 0 to 1 to the set of reals with the mapping f of x is equal to 1 over x. So let's mention some important characteristics of this function that we already know. The first characteristic is that we already know that f is continuous on this open interval 0, 1, which I will write that. And also, f is not bounded. It's not bounded on this interval 0, 1 as well. So we have a function that's continuous on its domain and a function that is not bounded on its domain. And our mapping is 1 over x. So a very important question is f uniformly continuous on this interval, yes or no, right? And is it being not bounded sort of helping it not be, or helping it to be uniformly continuous? Okay, so what do we need to do? So we need to pick any 2 points in our domain, and we, as usual, we need to let epsilon be greater than 0. And we need to look at the difference between any 2 arbitrary elements, in particular 1 over x and 1 over y that belongs to the range of our mapping. So doing a little bit of algebra, what do we get? So getting a common denominator, this is just going to be equal to y minus x divided by xy. And let's take the absolute value of that. X and y belong to the positive numbers, so their product is always positive. So we can also write this as 1 divided by xy times the absolute value of y minus x, which, as we already know, is the same as the absolute value of x minus y. So what do we know about this mapping 1 over xy? And keep in mind x and y are arbitrary elements. So we already know that this mapping is not bounded. So 1 divided by something, where that something is a variable, is not bounded. So keep that in the back of your mind for the next few seconds. So we know that we have complete control over this distance between x and y. So let's assume that that's going to be less than delta. So we're going to have 1 divided by xy times delta. And we need this to be less than epsilon. So we need to choose delta such that this inequality is true. So we can possibly choose delta to be equal to epsilon times xy. But what do we know? So delta is a fixed number. It's a fixed number in the set of reals greater than 0. And if it's a fixed number, keep in mind we have an unbounded function times a fixed number, so it's just a scalar multiple of an unbounded function. This function is also unbounded. So if we were to assume that there does exist a delta such that this inequality is true, then what we would have is a contradiction, because epsilon would be an upper bound for delta over xy. So that would be our contradiction, right? So if that is the case, what do we have? So that means that the distance between the images of x and y under f are not going to be less than epsilon for arbitrary x, y, and 0, 1. So that means that f is not uniformly continuous on 0, 1. So we have our first example of a function that's continuous on an interval, but not uniformly continuous on an interval. And keep in mind, if it's not continuous, it's not going to be uniformly continuous, so we don't need to consider that particular case. So let's see if we can construct an example of a function that is uniformly continuous on its interval. Obviously, a prerequisite would be continuous, so choosing a discontinuous function on its domain is not going to be helpful for constructing uniformly continuous functions. So what I want to do is I want to consider the mapping G, which is going to map 0 to infinity to R. Actually, let's make it a little bit more general here, so we can treat other examples as a corollary. Let's assume we have a to infinity. Let's assume that a is a positive number, and let's assume that G is the same mapping 1 divided by x. So my claim is that as long as we're staying away from the vertical asymptote of G, then we're going to have a uniformly continuous function. At least that's my claim, right? So what do we know? A couple little characteristics. Let's mention them here. So we already know that G is continuous on a to infinity, and if you don't know that for a fact, you can easily use the delta epsilon definition for continuity in order to prove. And we also know that G is bounded on this interval a to infinity. And the easiest way to see that is it's a monotonically decreasing function on a to infinity. So obviously the first term is going to be the maximum value. So we can say that the supremum of the set G of A infinity, right? So it's the set of all images of A infinity under G. You should be able to show that that's equal to 1 over A. And you should also be able to show that the infimum of this image set, A infinity, the infimum is actually just going to be equal to 0, right? Now keep in mind it does attain its supremum since we're working on a left closed interval, but it will never attain its infimum value. So it does have a max and it's equal to the sup, but it doesn't have a minimum, but it does have an infimum, right? So we have these two very important characteristics that I just want to mention before we get into the proof of our uniform continuity. So how are we going to prove that this function is indeed uniformly continuous on this left closed interval A infinity? So we need to be choosing arbitrary elements x and y in this domain. So let's assume that x and y belong to A infinity. So obviously the minimum value that they both can attain is going to be equal to A. And we're going to be letting epsilon be any positive number that one could give us. And let's look at the distance between x and y. So we're going to have 1 over x minus 1 over y. And as we've already shown in the previous example, this is equal to 1 over xy times x minus y. Now, it's very important to note that x and y are both bounded below by a. So if x is bigger than a, that means we have that 1 over x is going to be less than 1 over a. And similarly speaking, we know that y is going to be technically greater than or equal to a. So we know that 1 over y is going to be less than or equal to 1 over a. And here we have our x and y there. So what do we have? So we have that this is going to be less than or equal to 1 over a squared times the absolute value of x minus y. So we already know that we have complete control over this xy, so we know that this is going to be strictly less than delta divided by a squared, and here the choice for our delta may be very obvious to you. So we're going to choose our delta to be equal to a squared epsilon. So if we choose our delta to be a squared epsilon, we're going to have a squared epsilon over a squared, and that's going to give us our epsilon. So we have that if x and y belong to our domain and xy being arbitrary, then the distance between their images is going to be arbitrarily small. So what does that mean? So that means that G is uniformly continuous on our interval A infinity. So you may be thinking, well, 1 over x was not uniformly continuous on open interval 0 to infinity. So is it the unboundedness property of that function that's causing it to be not uniformly continuous on the interval? The answer is actually no. Just because it's unbounded doesn't mean that it can't be uniformly continuous on that interval. And let's do a very trivial example of that. So let's define h, which is going to map r to r, and let's choose the very trivial identity function h of x is equal to x. So a couple properties of this identity function. Obviously, h is continuous on the set of real numbers, and also h is not bounded on its domain, neither below nor above. So let's see if we can show that this function actually is uniformly continuous on R. So as usual, we're going to pick x and y belonging to our domain, and we're going to be assuming that epsilon is an arbitrarily small but positive number. So what is the absolute value between their images? So our images is going to be x minus y. Keep in mind that this is our f of x minus f of y. And we know that this is actually equal to the absolute value of x minus y. And obviously this is just our x and this is just our y. The reason I'm sort of writing this again is because I'm not looking at x minus y, the delta form first. I'm looking at the epsilon distance first, right? So since this is our distance between our images under our image function f, and we already know that we have arbitrarily control over this distance x minus y, so we know that this is going to be less than delta, then how are we going to choose our epsilon? Well, we actually can choose our delta to be equal to whatever epsilon we have, and that's just going to be equal to epsilon. And actually, technically, we can choose any delta that is strictly less than or equal to epsilon. So for example, we can choose delta to be equal to epsilon over 2, and that's perfectly okay. But if you want to choose delta to be epsilon, that's perfectly okay, as long as you have that strict inequality here. Right? So we have what? So the distance between arbitrary image elements in our range is arbitrarily small, in particular less than epsilon. So that means what? So that means H is uniformly continuous on its domain, even though the function is not bounded on its domain. Now, I think it's very important to notice the similarity that uniform continuity's definition has with the definition of what a Cauchy sequence is. So let's sort of recall what that is, because that's going to sort of motivate this next theorem. So we said that a sequence in the set of real numbers is a Cauchy sequence if for all epsilon greater than 0 there exists an n in the set of natural numbers. So this is practically similar to there exists a delta in the set of positive real numbers, because keep in mind natural numbers is a discrete subset of the positive reals, such that if m and n are greater than n, so obviously m and n are elements in the domain of our sequence, but strictly greater than n, then the distance between image elements of the sequence, so the sequence elements, is arbitrarily small. So Cauchy sequence definition and uniform continuity definition are very, very close to one another, and one can view that this is a motivation for our next theorem. So the theorem that I want to present to you now is the following. So let's assume that we have f which maps A to R, and let's assume that it's uniformly continuous on its domain A, and let's also assume that we have some sequence AM that is a subset of its domain, and let's assume that this is a Cauchy sequence. So keep in mind the things that we get when our sequence is Cauchy. If it's Cauchy, then it's convergent. Also, if it's convergent, it's also bounded. So we definitely have quite a few tools when we do assume that a sequence is Cauchy. Then if that is the case, then f of an, which obviously is going to be a subset of R, also is a Cauchy sequence. Right? So if we have a Cauchy sequence and we have a uniformly continuous mapping, then the image of that Cauchy sequence under this uniformly continuous mapping will also be a Cauchy sequence. Right? So let's see if we can provide a nice little proof for this theorem, because this actually gives us a nice tool to show that a function is not uniformly continuous. So let's assume that an is Cauchy on A, and let's assume that epsilon is greater than 0. Also, let's assume that f is uniformly continuous on our set A. So we're assuming our two premises, uniformly continuous and an being Cauchy. So what do we have? So by the definition of uniformly continuous, that means that there exists a delta bigger than 0 such that if x and y are arbitrary elements in our domain with absolute value of x minus y less than delta, then the absolute value of f of x minus f of y will be less than epsilon. Keep in mind, when we actually assume that this function is uniformly continuous, this delta that we have here has already been chosen. So we can actually choose this particular delta, or any one that's smaller, that actually instantiates the difference between the image elements under this function to be arbitrarily small. So let's just keep that in the back of our minds for just a moment. So since an is Cauchy, that means there exists an n in the set of natural numbers such that if n and m are strictly bigger than big N, then we have that the distance between an minus am are going to be less than delta. Keep in mind, delta is an arbitrarily small number, so I can pick these deltas to be the same exact thing because we have already assumed that the sequence is Cauchy, so we can choose those deltas to be the same exact thing. Also keep in mind that these, since we're assuming that we have n and m, these are just arbitrary elements that belong to our set A. So keep in mind, x and y are also arbitrary elements that belong to A, and an and am are not any different. So if that is the case, then since f is uniformly continuous, that means that f of an minus f of am will also be less than epsilon. Therefore, what do we have? Therefore, we have that f of an is a Cauchy sequence. Right, because that's the definition of Cauchy, right? Because that's just another sequence an, and that's just another sequence, let's call it am, right? So we can call it, for example, an is a Cauchy sequence. So how are we going to use this to prove that a function is not uniformly continuous on its interval? So let's sort of walk this through. So if f is uniformly continuous, and an is Cauchy, let's actually write that since we already used c to represent continuous. So if c is Cauchy, so if f is uniformly continuous and an is Cauchy, then f of an is also Cauchy. So let's look at the contrapositive for this particular statement, and that is the following. So if f of an is not Cauchy, and let's assume that an is Cauchy, so if f of an is not Cauchy, where an being Cauchy is still assumed, then that means that this function f is not uniformly continuous. Right? So that's practically the logic that we're going to use in order to prove that a function is not uniformly continuous. We're just going to pick a Cauchy sequence that belongs to our domain, and we're going to show that f of an is not Cauchy. The easiest way to do that is to show that, for example, it's not bounded, it's not convergent, and once we do have those two particular things, so that's practically your first, that's practically your second, and there is your conclusion that you are aiming for in order to prove that that function is not uniformly continuous on that domain A. So let's bring back that example that I did before, in particular where f maps 0 to 1 to R, with the mapping f of x is equal to 1 over x. So our goal is to show that this is not uniformly continuous on its domain 0, 1, but we're going to be using this little tool so I can show you how very powerful it is. So the first thing that I'm going to do is I'm going to choose my an to be equal to 1 over n, which obviously belongs to our interval 0, 1. And obviously we see that the limit of an is equal to 0, which means that an is convergent. Moreover, an is a Cauchy sequence because a sequence is Cauchy if and only if it converges. Now what we're going to do is we're going to do f of an and show that it is not Cauchy. So f of an is going to be equal to 1 divided by an, so that's the image of an under our reciprocal mapping f, and 1 over an is obviously going to be equal to 1 over m, which is going to be equal to n. And we already know that since this function is monotonically increasing and not bounded above, we have that the limit of f of an does not belong to the set of real numbers, which means that f an is not Cauchy. So we have a sequence that belongs to our domain, we have that it is Cauchy, we have that the image of that sequence is not Cauchy, therefore what? Therefore, this function, f of x is equal to 1 over x, that is delivering the image of our sequence to be a non-Cauchy sequence, is not uniformly continuous on the interval 0, 1. So if you're not a big fan of the delta epsilon definition of convergence or continuity, this theorem is actually very, very useful for you. So up to this point, we know what it means for a function to be uniformly continuous on a set, and we have a couple ways of sort of going about how to prove that a function is and also is not uniformly continuous on a set. There are several applications of uniform continuity, but we'll get to them at a later time. But now I want to introduce another type of continuity, which is called Lipschitz continuity. So, what is the difference between Lipschitz continuity, uniform continuity, and just basic continuity? So we already know that uniform continuity implies continuity, but not the other way around. And now I'm introducing this new type of continuity, Lipschitz continuity. Like, what does that mean? So, we say that a function is Lipschitz continuous on its set, or its domain, if, again, for any x, y in its domain, so the same basic thing as uniform continuity. Now, here's the new part. There exists a k in the set of positive reals such that the distance between the images is less than or equal to k times the distance between their associated pre-images x and y. Now, this definition might reminisce of contractive sequences, and if that is your observation, then you're probably right? So it practically places an upper bound as to how fast x and y's image changes underneath this image f, right? In some sense, if you know anything about derivatives, it practically places an upper bound on its derivative, and actually that's sort of what is going on here. Because if you do know anything about derivatives, if we rearrange this object, what you have here is the absolute value of f of x minus f of y over x minus y is less than or equal to k, and you should recognize this object here as the average rate of change of the function on the interval x, y, right? Which, as we already know, is just an approximation for the derivative. So we have that the average rate of change is bounded above. So that if the average rate of change is bounded above, and keep in mind this is for all x, y, and a, then we say that the function is Lipschitz continuous on its domain. Now, is Lipschitz continuity stronger or weaker than that of uniform continuity? And that's where the next theorem comes into play. So you may want to take a guess as to which one of these you think is stronger. So let's assume that f maps A to R, and let's assume that f is Lipschitz continuous, I'll abbreviate that by LC, on its domain A. If that is the case, then f is also uniformly continuous on its domain. So if that is indeed true, that means Lipschitz continuity is stronger than uniform continuity. So how are we going to prove that Lipschitz continuity implies uniform continuity? So if it is Lipschitz continuity on A, that means for any x, y, that means the absolute value of f of x minus f of y is going to be less than or equal to k times x minus y, where k is a positive real. And we already know that if we have this distance between x and y, we have complete control over that, so this is going to be less than k times delta. So keep in mind, k is going to be the constant that's true for all x, y, and a, so I can choose my delta to be equal to epsilon over k, and that's going to give us equal to k times epsilon over k, which is equal to epsilon. So if x minus y is arbitrarily small, we have that the distance between the images under this mapping is also arbitrarily small as well, and that means that f is uniformly continuous on its domain A as well. Right? So what exactly do we have for this sequence of hierarchy of continuity? So we have that Lipschitz continuity implies uniform continuity, and uniform continuity implies continuity. But we already know that continuity does not imply uniform continuity, so one may be able to guess that uniform continuity does not necessarily imply Lipschitz continuity. And if we go back to, for example, Cauchy sequences and contractive sequences, all contractive sequences are Cauchy, but not all Cauchy sequences are contractive. So we're practically having that same exact hierarchy as we had before. Right? Now, before I get into an example of a function that is uniformly continuous on an interval but not Lipschitz continuous on an interval, I want to first present a very important theorem that we're actually going to use in its justification, and it goes as follows. Suppose that D is a closed and also bounded interval. For example, closed interval 0, 1. And let's suppose that F maps this closed and bounded interval to the set of reals. And let's also assume that F is continuous on its domain. So we have a function that's continuous on its domain, and its domain is a closed and bounded interval. If you have this, then F is also uniformly continuous on its closed and bounded domain, D. So every continuous function whose domain is a closed and bounded interval will always be uniformly continuous on that domain. And that's actually very, very interesting. So the proof of this requires a couple other mechanisms that don't quite fit in this narrative. In particular, if you have theorems associated to what is called compactness for sets, then the proof of this actually might not be that difficult, but we'll get into compactness at a different time. So let's just take this theorem as fact and not present the proof of it, and actually use it to sort of show how it can be used to show that a function is not Lipschitz continuous, but is continuous. Uniformly continuous on its interval. In particular, let's consider the interval 0, 1 that maps to the set of real numbers with the mapping f of x is equal to the square root of x. Right? So what do we know about this function? So let's investigate this a little bit. So we already know that f is continuous on the interval 0, 1, and we can easily prove that with the delta epsilon definition if you desire, but we already know the graph of it, so if you assume that your intuition is correct on graphs, then it's obvious to see that this is indeed continuous. Also, if we go on the closed interval 0, 1, since we have a monotonically increasing sequence, we also have that f is bounded on this interval as well. But we don't really care about the image being bounded. The only thing we really care about is its domain. So we already know that since 0, 1 is a closed set, so that's the first requirement, and it's also a bounded set, it's a closed and bounded set, that means by this previous theorem, f is uniformly continuous on the interval 0, 1. So if you have a continuous function on a closed and bounded domain, then the function is uniformly continuous on that domain. So now what we need to do is to show that this function is, or is not, Lipschitz continuous on its domain. So let's actually assume that f is Lipschitz continuous on 0, 1. You're like, well, how can I assume it? Isn't that what we're trying to prove? Well, obviously, if I'm assuming it to be true, I'm probably going to go for a contradiction, implying that it's not. So if f is Lipschitz continuous, that means that there exists some number k in the set of positive reals such that the absolute value of the square root of x minus the square root of y is less than or equal to k times the absolute value of x minus y, and that's going to be true for all x, y in the interval 0, 1. So that's if it is indeed Lipschitz continuous. So what I want to do is I just want to rearrange this object just a little bit. So I'm going to divide both sides by this object, and let's assume without loss of generality that x does not equal to y, else you have that trivial thing that I mentioned earlier. So once we have that, we're going to have that 1 is going to be less than or equal to k times the absolute value of x minus y all over the square root of x minus the square root of y, for which we can easily factor into k times the absolute value of the square root of x plus the square root of y. And now what I'm going to do is I'm just going to rearrange this a little bit. So I'm just going to move that back to the left-hand side. I just wanted to show it on the right-hand side because some people can't see that on the surface. So once I rewrite this, I'm going to have that k is going to be greater than or equal to r 1 over the square root of x plus the square root of y. So we have this inequality, and this is obviously, again, going to be true for any x, y in the closed and bounded interval 0 and 1. So what do we know about 1 over the square root of x plus the square root of y? Keep in mind, x and y can get close to 0 arbitrarily. right, for this particular object. So if that is the case, one can easily show that this is not bounded above. Because if you think about it, we can fix one of those particular x's. For example, we can make y arbitrarily close to 0, and we can make x get close to 0. And we already know that that goes to infinity. So if we can show that this is not bounded above, which one can easily show, then us saying that it's less than or equal to k actually gives us our contradiction, right? So those things contradict each other. So if that is the case, then what do we have? So that means that f of x equals the square root of x is not Lipschitz continuous on the closed and bounded interval 0 to 1. So uniform continuity does not imply Lipschitz continuity. And again, there's several applications associated with Lipschitz continuity, just as there was for uniform continuity, and we'll get back to them at a later time. So the last thing that I want to end this conversation with is another type of continuity, and let's see what this type of continuity says. So we're going to be letting f map A to R. Then f is said to be Holder continuous of order alpha on A if for all x, y, and A there exists a k in the set of positive reals and also an alpha bigger than 0 such that the absolute value of f of x minus f of y is less than or equal to k times the absolute value of x minus y. And if I leave the definition there, you're going to be like, well, isn't that just Lipschitz continuity? And the answer is yes, but now we're going to put an alpha exponent on the distance between x and y. Okay, so this is what we refer to as Holder continuity of order alpha. Obviously, if we have that alpha is equal to 1, we clearly see that that implies Lipschitz continuity. But if we choose any alpha aside from 1, like 1/2 or 3/2 or pi or the square root of 2, that does not necessarily imply, or maybe it does, uniform continuity and so on, right? But again, Holder continuity has its own set of applications, which we'll get into a later time. And I'll sort of let you explore, is it possible for it to be uniform but not Holder? Is it possible for it to be Holder but not uniform? And all those types of things. So I hope you enjoyed this video where we exposed you to some different types of continuity, in particular uniform, Lipschitz, and Holder continuity. Hope you enjoyed this video, and I'll see you in the next one. Take care.
Thank you.